So here, so from this claim, we can show this is in this relation R. So in fact, we also need a CA hash for this relation R. And this, so in this construction, we need a CA hash construction for this relation R. And so this follows from the, so for this kind of CA hash, it follows from the work. So it almost can handle all of the sparse relation up to some parallel repetition. So I will not go into the detail of this work. So if you are interested, you can read it yourself. So this is the work. So it's a CA hash for efficiently verifiable product relation. It's the beautiful work by. So this is the home HLR, Holmgren, Lombardi, and Rosblum. Okay. Okay, so finally, so let me ask a question. Okay, yeah.
Could you say again why we need, like, why the CIH we saw in last week's class isn't good enough?
Right, good question. So last week, the CA hash you saw is for searchable relation. So that means the relation, so the relation here, so the CA hash relation here, so the relation here need to satisfy the searchable property. So it means, so this beta, so for any fixed alpha, there exists a unique beta such that this alpha beta is in this relation R. And moreover, there is an efficient algorithm, some efficient algorithm F, such that it can take this alpha and output such a beta. So that's a efficiently searchable mean. So here it's possible that for a fixed alpha, there might be multiple beta that can satisfy this relation. Because for a fixed PCP, there might be multiple queries that can make the PCP be accepted. Yes, good question. Yeah. So what HLR shows that if the sparse relation has an efficient verifier algorithm, then then you can build a CA hash for them up to some parallel repetition. Yeah, roughly speaking, it's a yeah. So okay, so now we have a construction of snarks, but let's see what's the proof size for this snark. So the proof size consists of the first message and the third round message. So the first round message consists of L of hash values. So you can think each hash value is also a FHE ciphertext. So it's a polylambda bits. So in total, the first round message consists of poly C times poly L. But it's independent of the K. And the third round message is K times polylog C times poly L. Because for each, in the third round message, for each instance, you send Q PCP answers. So the size of Q is lambda times polylog C. So in total, you send a K of them. So in total, it's K times this. Okay, so this is already non-trivial because it's so this number it could be much smaller than K times W. So right, because the second term is almost order of K, and the first term is almost C. So yeah, so this is already non-trivial, but it's still large. So so the big issue is if you look at the verification time. So the verification time is ULC is K times poly C. The reason is the verifier need to verify the PCP answers for each of the instances. for x1 to xk. So so in this step, so each PCP verification need to take c time, and in total it need to take k times poly c. Yep.
Why is there a poly lambda at the end?
Oh, so that's because each query is so each query. So if you remember, yeah. So here, so each query size is lambda times polylog c.
Oh.
Yeah. So it's yeah.
So they're not just querying single bits; they're querying like blocks of links.
Right. So here we have a lambda term because we need to do the parallel repetition. So you take a PCP with constant soundness error, and you amplify it lambda times by parallel repetition.
And you want to amplify it because you want complete, like perfect completeness or something? Or?
Yeah.
Okay.
So you can have PCP with perfect completeness. Yeah. So you don't need to worry about when you do the parallel repetition. Okay. So the verification time is still very large. So in fact, you don't have any savings if you do this directly. So on the verification time. So let's consider for a general snarks for batch NP or BARGs. So what's the verification time? So remember, the verifier in a BARG, the verifier need to read at least the CRS and all of the statements to verify the proof. So the verifier need to at least read all of the instance. So it seems that there is a lower bound on the verification time. The lower bound is just at least k times x. Okay. So next I will show you how to reduce the verification time and the proof size of BARGs. But we will first right. So we will consider a variant of BARG, and it don't have this lower bound on the verification time. So the idea, so I will define a new notion of BARGs. Let me erase this. So in this notion of BARGs is called, it's called index BARG, or you can also call it a snarks for batch index. So the idea is. So in the original definition of BARGs, the verifier need to read all of the instance because the instances are non-uniform. So in this notion, we will consider a special case when these instances are uniform. So intuitively, it means there exists some circuit U such that the ith instance is generated by using the circuit U and the index I. So intuitively, it says the instance can be described in a uniform way by only use the index. And if this is the case, then what the prover will try to prove is x1 to xk is all in this language L. So now it is equivalent to say, so for each index I, there exists a witness wi such that this circuit C and ui wi equals 1. So then we can define. So essentially, this is you can view this as a new NP relation. So the new NP relation is defined as follows. So the instance is just an index, and it verifies there exists a wi such that. So this is just a rewriting of this, right? So this right. So, and you can view this as a new NP verification circuit that some C prime. So it only takes Wi and I and Wi as input, and it internally computes this U and verify C. So this inspires us to define a new notion called index BARG. So an index BARG definition, an index BARG is a BARG for this kind of relation. So it is for this kind of language, where the language is just some general NP language, but the instance is treated as an index. For this language. And the prover, so the prover, we still have a CRS, and the prover tries to convince the verifier that all of the indices from 1, 2, etc. to k is in this language. So the honest prover only need to read index k, and it has a witness from W1 to Wk for each of the index. And the verifier only need to take k as input. So now the verifier, so this k can be represented as log k bits because it's just an index. So what's the best verification time we can hope for? Anyone knows? So, good. So the verification time is so the verifier only need to read this index k and the proof. So the verifier can be as small as verification time only need to be some log k. Can be as small as this much. Some log only depends on log k and the lambda. So okay, so this is right. And for this index BARG, we also require the completeness and the soundness in the same way as before. Any questions? Yeah.
How should I think of this U? Like, should I think of it as being part of the instance or something locally defined?
Yeah.
Of it,
So you can think it's yeah. So you can think it is you can always observe it in the relation circuit. So you can think it's part of the relation.
Right. I guess, are you going to pay for the size of the description of U anywhere, or is that?
Right. Good. So the verification circuit, in fact, need also to depend on C, right? Because the verifier need to read the circuit.
I see. And is there like a unique instance to this problem then? What, like, or you're saying K itself is the okay?
Yeah. So now the point is now the verification time don't depends on linear in K. So previously you need to read all of the instance, and now you the verification time only grow log in K. Yep.
Are we supposed to think of C as part of the input?
C as part of the input.
So like, or I guess C prime, which like stores U in it.
Right. Yes. Right.
Okay, so that is part of the input. So then how would, so V still has to read what C prime is. So would that take a lot of time?
Yeah. So you can. So it depends on how you define it. So you can define it for a fixed C, and you have such a proof system, or you can define a proof system for any C. Then you need the verification time to grow with the circuit size C.
Isn't defining it for a fixed C kind of like not that helpful because we're just solving batch snark for like a fixed set of x's?
But you can choose C to be universal circuit. Then it's yeah. Then it's general. Good question. So in fact, right. I think yeah, if you take a university, you need to use the U maybe. Yeah. Yeah, it's good to think C as the input. Yeah. Okay. So, so in the remaining time of this lecture, we will prove the following theorem. So there exists a index barg from LWE, and the proof size is poly log. So it will grow log in k, c, and lambda. And the verification time is log k, c, lambda. Okay, so both of them are almost match the best you can hope for, up to some polynomial. So, and okay, so here I want to emphasize the. So I want to emphasize here that in fact you can, if you know how to build this index barg, then you can build BARGs with almost the same verification time and proof size. So in other words, in fact, a batch of instances are without a loss of generality uniform in some sense. So, so what I will show you is, in fact, if you know how to build index barg, then you can use it in a generic way to build BARGs. So the reduction works as follows. So suppose you have, so now we want to build a BARG for a bunch of instances from x1 to xk. So the idea is we will first build a Merkle hash of all of the instances. So, and we have some hash root. So now we have the prover send this hash root to the verifier, and prove that, and then we have the prover to show that for any index I, there exists a local opening. Row I. So the local opening, remember, is the root to leaf path for each of the leaf. Okay, so there exists local opening row I for xi, such that the local verification will pass for this xi. Local verification. So the local verification algorithm will take the hash root and the index I and the xi, which is the open value, and also this local opening, which is the root to leaf path. And moreover, there exists a wi such that the original circuit is satisfied. So the idea is you just hash all of the instance from x1 to xk, and you send the hash value to the verifier. Then you prove for each index I, there exists an opening xi to this hash, and this C of xi is satisfied. So in this way, you convert so you convert a batch of NP instance to a index, to a batch index instance. Because so now the statement only grow, so it proves something for each index I. So you can view so you can view this part. So you can view this part as some circuit C prime. So C prime will take index I and witness row I, Wi, and check the two things. Then you can generate a index barg for this instance, for each of the instance from x1 from 1 to k. So and this and then you generate an index barg for this kind of instance. So now you send this to the verifier, and this is your barg. Yeah. So okay. So if pi is small and the h is small, then your total proof size is also small. So that's the idea. So next, I will only focus on. So I will come back to this point later, when we. So because the proof of soundness of this transformation is not trivial, because in fact you will see this is not a. So the non-adaptive soundness previously is not sufficient to prove the soundness, because this circuit will depend on this hash, and is chosen adaptively by the adversary. So we will come back to this point later to show how to prove the soundness of this transformation. Okay, so next I will show you how to build this index barg. So our starting point is still this protocol. So as I just said earlier, so the first round message is small because it only depends on C, but the third round message is large. So how can we further compress the third round message? Okay. So in the context of the index barg, all of the instances are just indices. So I can replace them with 1 to k. And the idea is we're going to remove this round message. We're going to remove this round of message. And so we're going to delegate this the verification of this message to the prover. So the prover will have this open queried columns in his hand, but he is not going to send them to the verifier. Instead, the prover is going to do the verification by itself, and prove to the verifier those verification is indeed correct. So the conjunction works like this. So the prover still send this H1 to HL to the verifier. And the prover is going to compute this PCP query using the CI hash. And then the prover and the verifier is going to run another protocol. So another snark. And this snark, on the prover side, he's going to use the columns, the opened columns, as the input to this protocol. And in the end, the verifier is convinced that this the third round message verifies. So what does this mean is, the prover is going to prove for. So the prover is going to prove for there exists. The prover is going to prove to this verifier in this protocol the following language. So there exist columns Q such that two things. So one is for each column, for each Q in the queried set, the hash is computed correctly. It's consistent with the first message. So the HQ is the SSB hash of the column, the QS column. So I omit the SSB key here. Okay. And the second, for each PCP, for each instance, so for any I in K. So here, the instance is just the index I. The ith instance xi is just the index I. So he will verify this. So the PCP verification of I Q. Yes. And the Q's column, the ith coordinate of the Q's column, and we collect them together. Okay. So this is the statement this protocol wants to prove, and the prover is going to supply it with the witness, which is this. Okay. So that's the high-level idea. So, but to achieve this, so suppose we can rewrite this statement as a batch index statement. Then I can apply the same construction again on top of this statement. So we can apply the same thing again to this new statement, and I can do the recursing. So that's the idea. So how do I? But the issue is how do I represent this as a batch index language? So how do I represent it as a batch of index language? So how do I represent it as a batch of index? So now you can see, maybe you think, okay, so this is almost an index language because this is, at least this part is, this is clear for any index I. So, right, this is for any index I in K, there is something. So this is similar to our index language, but this part is not clear. So the reason is Q is very small. But the NP witness is very large. So if you treat this Q as an instance, then the witness size is K, because each column has K entries. So for each column contains the PCP coordinate for each of the instance. So the column size is K. But if I treat this column Q as a witness, then when I do the recursion, the proof size will grow with the size of K, because again I will have this kind of hash values, some L prime, but those H1 to L prime, H1 prime to L prime prime, so they are for the new protocol and the new instance, so they will grow with the size of K. So that's too large. We cannot afford that. So next I will rewrite this instance as a batch of statements, and the statement size will be K, but the NP witness will be small. Okay, so how do I rewrite it? So let's look at what this verification do. So for each of this verification, we have a column Q. and its size is k. So it will recompute this SSB hash and check if it's the same with some HQ, which is the hash value sent in the first round. So the idea is that suppose this SSB hash, suppose we have some more structure of this SSB hash, then I can local verify it. So that means if I build this SSB hash with some, so let's see. For example, if the SSB hash is built in a Merkle tree, as a Merkle tree, then I can replace this verification by verify that for each index I, in K, there exists a local opening, row IQ. So row IQ is the local opening for the, you can think for each index I have an entry. The entry is column Q, the ith position of the column Q, and I have a local opening for that, Q, row IQ. So I only need to show there exists such a local opening for this hash. So here HQ is the hash value, right? So for HQ, yeah, I only need to verify this. So now I get a batch of NP instance. Right. So yeah. So let me rewrite this. So suppose I have a SSB built in the Merkle tree way, then so the protocol will work like this. So initially we have H1 to HL, and we have this Q. So in the new protocol, we are going to, the prover is going to supply with the queried column for this Q, and also a bunch of local openings for each coordinate in this Q. Okay, so and this protocol will prove. So this protocol is a new index BARG protocol. It will prove for a new instance L, for new language L prime, let's denote it. So L prime, it contains all the index I. And for each index I need to show there exists a witness, which is column Q I. So this is the ith PCP answer, and their corresponding. I also need this Q row IQ. Such that. So first I need to verify the PCP answers, right? And the second, I need to verify the local opening is correct. So I need to verify so there is some local opening verification algorithm. The local verification algorithm will take the hash root for each queue. And so I need to verify this for every queue. And this local verification algorithm of SSB will verify row IQ. Yeah. Any questions? So this is the new. So this is the new instance, new L prime. So for each I, and so the prover need to prove, so the prover need to prove 1, 2, etc. to k are all in this L prime. Right. So, yeah, any questions? Yeah.
So just to be clear, we're going to recursive this, and the idea is that the number k has remained the same, but then the witnesses are not growing.
Good question. So if you do this recursion, it will loop forever because from the beginning we have k instances, and then in the next level of the recursion we still have k instances. So
Yeah, I mean, could you like bunch it up maybe, like you see what it
exactly. So that's what we will do next. Any question? Yeah.
So HQ is the hash of statements?
Sorry?
HQ.
Oh, right. So HQ is part of the statement, right? So
Is it the hash of the statement x1 to xk or?
so you mean where is the XQ, where is HQ comes from?
Yes.
Oh, good. So HQ is the same as HQ here. So you have, so initially we have a bunch of statements from 1 to k, and each of them has NP witness from omega 1 to omega k. And we arrange this, we compute this PCP matrix. And for each column, we hash it to H1 to HL. So, and the HQ is just the Q's column of this H1 to HQ. Yeah. The index Q among this H1 to HQ.
And I assume the local opening version of the SSB is some variant of the FHE thing with like a Merkle tree
Good.
inside or something?
Yeah, so that's what I'm going to talk about next. Yeah, so now you may ask, so how do we construct such a SSB with Merkle tree style construction? So because the construction I just showed you doesn't satisfy this property. So this is a SSB. So SSB with this local opening property. So what it says is, so the idea is, so if we build the hash like a Merkle tree, then we have this local opening. So for example, and the issue is how do we still have the somewhere statistical binding property? So the idea is just so at each node of the tree, we're going to pick under the hood of FHE one of its children. So you can think initially we have some x1 to xk in the clear, and we'll have some. So at each level, we're going to pick either its left child or right child for each node in this level. for example, in this level, so suppose this is your index I, then what we can do is for each node in this level, we're going to pick the left child. And at this level, we're going to pick the right child. So at each level, we're going to have some FHE homomorphic encryption of some bit. So some bit B1, and so let's say this is B2. And each level, we're going to homomorphically evaluate this using this B1 and B2 to pick the children under the hood of FHE in the same way as before. So this can give you SSB with local opening. Okay, but what we will so one property we further require about this SSB is the local opening correctness. Okay, so we require this property because remember in the soundness proof, we need to ensure if the proof is accepted in the third round, then the proof contains some opening of the SSB. And we need to show this opening must be consistent with the SSB extracted value. So originally, this is easy to ensure because the verifier sees the entire opening. But now it's not clear whether this can still hold, because so now the verifier only sees a local opening of the SSB. Okay, so it does not sees all of the x1 to xk. It only sees the root to leaf path of some xi. So we need a further local opening correctness. So the correctness of local opening says that so this SSB with local opening has some local verification algorithm. So it will take the hash root h and some index I and the xi and the root to leaf path for this xi, and it can decide whether to accept or reject. Okay, and the local opening property says that for any index I, h, xi, and rho I, so if this local verification passes, then it must be case that the extracted value of the hash equals this xi. So here, the local verification. Let me see. So the local verification also need to use the SSB key to check this. Okay. So here, if this is true and the SSB key is generated for the index I, then I need if the local verification passes, then the extracted value must be xi. So this is not trivially correct. This is not trivially holds if you use just this construction, because a malicious phi, it will contain the root to leaf path to this xi, but it also needs to contain the siblings of this. So in this authenticated path, it also needs to contain the siblings of each node in the path. But those siblings may not be well-formed FHE ciphertext. So indeed, you need to further add some bootstrap mechanism here. So you need to homomorphically encrypt so at each level of the FHE, you need to use a different FHE key. And at the next level, you need to homomorphically decrypt the FHE ciphertext at the previous level to ensure it's a well-formed ciphertext. So I'm not going into the detail, but you can you can fix this easily by your own. Yes. Okay, so now any question with this construction? Yeah.
Why are we now using SSB in a Merkle tree style instead of?
Good question. So if you directly use SSB in a Merkle tree style, maybe there is some separate text size blow up. So each time so each time the separate text size is lambda times larger, and yeah.
But I mean, in this new version of index bar, why not when we hash the column?
Yeah.
We hash it in the Merkle tree side instead of hashing it in one.
Right. You mean we don't hash it as entirely? We hash in the Merkle tree style.
Yes.
Yes. That's what we are doing. Yeah. Okay. Any question? Okay. So if you do this construction directly, then this construction will loop forever because the recursion will never end. So initially we have k instances, and at the next level it still has k instances. So next, what we will do is we will use a 2-to-the-1 trick to reduce the number of instances each time. So let me. So let's denote the. So let's denote this circuit. So this part of the circuit as some C prime. Okay, some C prime. So C prime will take some index I, and the witness Wi prime. So the witness Wi prime corresponds to this part. So this part is the Wi prime. Okay, so the 2-to-the-1 trick is this. Suppose you have k instances. So for now you want to verify all of them are so you have instance from 1 to k, and their witnesses are W1 prime to WK prime, and you want to ensure. So the prover wants to prove to the verifier that all of them are correct, are in this language L prime. Okay, so what you do is you look at any two adjacent indices, instances, and just combine them. Okay, so now the combined instance is still 1, but it's but the witnesses are concatenated together. So you have this W1 prime and W2 prime, and the next two instances are W3 and 4. So you have this 3 prime and W4 prime, and the final one is K and WK. So you combine each adjacent one to get the second instance. And then you do this for any two of them. So in the end, you have k/2 instances. But the cost of doing this is the size of the witness will blow up by a factor of 2. So okay, so now we obtain. So let's say the original language is L prime. So it contains of I such that there exists Wi prime. So now, so C prime is the verification circuit of L prime. Then here, the new instances is the following. So it defines a new language L prime, L double prime. So double prime still contains of I, but the witness are 2i minus 1 and 2i and w2i 2i prime. So this concatenated witness is the new NP witness for this L double prime, and you need to verify C prime of this 2i minus 1 w2i minus 1 is 1, and also 2i and 2i is 1. Okay. So by doing this, the size of the number of the instance will half each time when you do the recursion. So in fact, we will prove this for L double prime, and we only prove for 1 to k by 2. They are all in L double prime. Yeah. In the recursion. Yeah. So that's what we will do. Okay. So now the question is at the end of the recursion. So at the end of the recursion, each time, so at each level of the recursion, the number of instances will halve. So at the end, there will only be one instance. So what will we do at that point? Anyone knows? Yes, right. So we directly send the witness, and the verifier can verify it. Okay. So now let's calculate the. So this is the construction, and let's calculate the proof size for this construction. So initially we send those H1 to HL, and that cost. So the size of that is poly C. Right, poly C and lambda, and we have this Q computed by the CI hash. But at the next level of the recursion, so at the next level of the recursion, we will also have this first round message for that. So let's denote it by hi prime. So what's the size of this message? So remember, this is the index barg for L double prime, and it has circuit, the verification circuit C double prime. So what is the size of this message? So this is efficiency. Yes. So in the next level of recursion, we'll do the same for using the same protocol. So originally the NP verification circuit is C, so we have first round message this much. So in the next level, the NP verification circuit is C double prime. So the size of this message is poly C double prime lambda. But there is an issue if you do this recursion directly. So let's examine what is the size of C double prime. So C double prime will contain, so each C double prime will contain 2 copies of C prime. Right. So C double prime. I should say, okay. So right. So I should say this is the. So this is the C double prime. So, right. So it will take index I and this as the witness, and verify these two things. So the size of the C double prime is roughly 2 times C. And so what is the size of C? C prime. So the C prime. So C prime is here, so C prime, the first part of the C prime is the PCP verification. So here we will have an issue because the PCP verifier need to know what is the, he at least need to know what is the NP relation. So the PCP verifier runs in C time. Right. So we will have an issue here because the C prime is roughly C, at least C. So if we do this directly, so you can think at the top level we have this poly C, and at the next level we have this poly C prime, which is 2C. So this is 2C, and at the next level of recursion we'll have 4C. So we will have log k level of recursion because each time the number of instances half. So the number of so the depth is log k. So in the end, we have k times c, which is large. So the proof will grow with k times c, which is large. So the final idea is we are going to use a PCP with some special property. So this kind of PCP has this online-offline verification property. So this is called PCP with fast online verification. So those PCP has the property that, so for any PCP prover and verifier, so given any NP instance X and W, you can generate a long proof, right? So this is just a normal PCP, but the verification algorithm of the PCP has more structure. So the verification algorithm, so originally the PCP verifier need to verify for X, Q, and the PCP Q. So now the PCP verifier can be decomposed to two parts. So first, so there is an offline pre-processing phase. So the pre-processing phase only depends on the relation circuit C. Okay, so this is a PCP for the language L. So the pre-processing phase will take the relation circuit as input, and it will use the query to generate some state. And this state will only grow. The size of the state is polynomial in X. So the point is, so in some case, when the relation circuit is very large, so the pre-processing phase will run in the size of the relation circuit, but it will output of a very short state. And secondly, in the online phase, there is an online verification part. So the online verification will only use such a short state and the X, and the Q, and the PCP verification, and the PCP answer to decide whether to accept or reject. So the point is, the online verification phase only depends on so it's a polynomial time algorithm. So which means it only depends on X and the size of Q. Okay, so you can imagine if the C is a very big circuit and the X instance is small, then this means the pre-processing phase will take most of the time, but the online verification will be very fast. It only depends on the instance size and the size of the query. So this property is satisfied by most of the algebraic construction of PCP. So yeah, any questions? So I will not go into the detail because so in fact this property is used in many practical snark construction, because in the practical snark construction they also need to use PCP or some form of the PCP, such as linear PCP. So in those construction, you also have the problem that the relation circuit is very large, but you want the verification to be small. So what they do is they can do some pre-processing on the relation to generate some short verification state. And given the verification state, you can verify the statement in a short time. Okay. So now we will use this PCP with this further with this property, and then we can then we can further modify the construction to only do the online verification here in C prime. Okay, so. So what we will do here is we first generate the CI hash using the CI hash to generate Q, and then we do the pre-processing to this Q to generate some short state. And this will use the relation circuit C. So we can do this because we use the same PCP query for all of the PCPs. So right. So it's for all of the PCP, they are using the same PCP query. So I can do this pre-processing. So once I have this state, this short state, I can hard code it in this construction of C prime. So I'll replace this with the online verification. Oh, sorry. So this is a local verification. So this is online verification of the PCP. So it will take the state and of the rest. So now this will solve this recursion issue because now the circuit C prime will not depend on C. Instead, it will be polylog in C. The reason is that so here, you can check here because the C prime will. It will only involve the online verification. So it's a polynomial of it's a polynomial in the length of I, which is log k, and right. And the local verification of the Merkle hash is also small, so it's also some polylog in k. So that you can check is so this is polylog log k and lambda, and you can take this recursion inside of this analysis and see finally the proof size is only polylog in. So the proof size is the total proof size is polylog in C and polylog in k. And the polynomial in lambda. Yeah.
Plus the length of one witness, or I guess that's also fine. Like the base case that you send the witness, right?
Yes. So in fact, after you do this once, so at one level of the recursion, the witness is already very small. So because the witness is just the PCP opening, so it's a polylog C. So finally, at the end, the final level witness is also very small. So I probably don't have time to cover all of the security proof, but I will show you the most important part of it. And so how do we prove the security of this construction? So now the construction is here. So to prove the security, it's natural to use so suppose we have some security of this index BARG, then maybe we can use it recursively to prove the security of the entire construction. But we have an issue here. So the issue is L double prime, it will depend on the first message. Because so L double prime will use this L prime, so this C prime. So this C prime will use the hash root, this HQ. So this hash root comes from this hash value and of the H1 to HL. So this means the adversary can potentially choose this choose the next statement depends on the CRS, because CRS is first sent to the adversary. So this is not captured by the non-adaptive soundness before. So we need a new definition of soundness. And the issue is that we don't know how to achieve fully adaptive soundness. So the adaptive soundness means that the cheating adversary can choose the instance depending on the CRS. And so what we prove is some semi-adaptive soundness. So this soundness notion is not only important in this security proof, it will also be crucial for your next lecture. So when you compile this batch index of snarks 4p. So it defines as follows. So it says that, so it allows the cheating prover to choose the relation circuit, but it cannot choose which index to cheat. So let me define it. So we say index BARG is sound if there exists so first I need another key generation algorithm, CRS generator. So I'll call it generator bar. So it will take the security parameter as input and index I star, and will generate some CRS star. Okay, and I require and this CRS generator is indistinguishable with the real CRS. And furthermore, for each non-uniform PBT adversary, cheating prover P star, we need to have the following property. So P star, when P star receives the CRS generated by this generator star, it can choose as relation circuit C and a maliciously chosen relation circuit C and a pi star, such that the probability that the verifier accept for this K and the IS instance, the I stars instance is not in the relation circuit defined by this C star is negligible. So yes, so the intuition is that, so suppose the intuition is that the SSB is binding for some location, for some instance. So you just set the generator bar as the generator that output that kind of SSB. So the SSB will be binding for the I stars position. Then you cannot cheat for the I sparse instance, but you do have the option to, so the cheating prover can choose a different circuit, relation circuit C, but it cannot cheat for those the I stars position. Right. So that's a semi-adaptive soundness. So to prove this soundness for this construction, the idea is that so for any I star that is not in the language, so you can see so from the correlation intractability, So essentially the idea is that if I star is not in the language, and for any cheating proof, right, so you just switch this generated bar for this I star. And you can argue if I star is not in the language, then I star over 2. So because we do the 2 to the 1 trick, so it will translate to a new instance at the next level. Then it's also not in this. It's also not in the L double prime. So if the adversary doesn't cheat for the CI hash, so that's the ideal. So that means the so for any so if it's not in the so if the query and the hash values output by the cheating prover does not satisfy the CI hash relation R, then you have this. Then if the I star's position is false, then it translates to another new false statement. So you can use this claim to inductively argue that initially, if you have some fixed I star, then you can track this fixed I star at each level by divided by 2 and round up to it. And finally, you can catch it because the last statement. So in the last level of the recursion, you just send all the witness. So you must be able to catch it. So that's the idea. Okay, so that's all about the class today. Yeah. Any questions?
So does the full construction get any form of like the whole construction?
Mm-hmm.
Yeah, any sort of adaptive soundness, or is it like?
Yes. So it only gets this kind of adaptive soundness.
I see, like some notion of this for general BARGs as index languages or something.
Oh, so for the index BARG, we can get a semi-adaptive soundness.
Right.
And for general BARGs, I need to. I think it also has some similar notion. I think.
Can you make it that, like, is there some other construction that's adaptively sound, or is it a very tough thing to do?
That's a good question. So in general, so given any non-adaptive sound snark, you can always upgrade it to adaptive sound by using complexity leveraging. So, but you will pay 2 to the instance size in the security proof. So, but in the BARGs, if you to the total instance size is k times x, so it's very large. So, yeah, I'm not sure you can really do that.
I see. Like, is it clear a priori that like Gentry Weeks only applies to adaptively sound?
Right. So, right. So there seems to be a gap, but I'm not sure how large is the gap.
I see.
So, yeah. So maybe maybe you can use some clever complexity leveraging to almost close the gap, for example.